Okay, so if I remember correctly, the last time we were here, we were discussing titrations and the different titration curves. And I think we worked in one example. Please correct me if I'm wrong, but I think we did this example right here. Did we? Yes, no, maybe so. I think we did this one. So let me just move on now to a discussion of indicators. Indicators, acid-base indicators, are basically weak acids or weak bases that takes on the color of which reflects the pH of the solution itself. So basically, the acid or base, weak base, will have one color under acidic conditions and then another color under basic conditions, right? So this here is basically showing you, assuming that the indicator is a weak acid. This would be the dissociation, of course. And what will happen is that this substance, HIN, the undissociated molecule, will have one color and the conjugate base will have another color, right? And basically by adjusting the H plus ion concentration, we can favor one over the other, all right? So for example, if the solution is such that the concentration of the undissociated molecule is greater than that of the conjugate base of that molecule, to the tune of this here, where the ratio is greater than or equal to 10, then the color of the undissociated molecule will predominate. On the other hand, if it's the reverse, where the concentration of the IN minus is less, or I should say greater than that of the undissociated molecule, then basically the color of the conjugate base will predominate, right? So if this ratio is less than or equal to 10, then basically the color of the conjugate base would determine the color of the entire solution, right? And below that, we have some indicators and their corresponding colors in acid and base. And for those of you enrolled in my lab, you should be familiar with phenolphthalein, which has a color of colorless in acid, but pink in base, all right? And what you'll find is that different indicators will transition from one color to the other over a particular pH range. So in the case of phenolphthalein, the pH range over which the color change will occur will be from 8.3 to 10.0, and you see other pH ranges for other indicators. So this is just basically a dye that has been extracted from cabbage, which can also perform the role as an indicator. As long as you know what the pH ranges are for the color transitions, you can actually use the color of the dye extracted from cabbage to basically tell what the pH of a particular solution is. Now, when you're doing a titration, such as the ones that we talked about earlier, it's important that you know exactly where the equivalence point is. Now, you can determine that by using the pH meter, right? So while you're adding your, let's say, base to your acid, the pH will increase and you're continuing to measure the pH as you continue to add more base and so on, and therefore you get this curve. But in some cases where you do not have a pH meter at hand, or you don't want to use a pH meter, what you need to do to find the equivalence point is to basically use an indicator whose pH color change range falls within the big leap in the pH as you go from here to here, right? So in the case of the titration here, and I think this is a titration, yes, strong acid versus strong base, where the pH jump goes from here to here and the equivalence point is 7. The indicator that you would use for this purpose would be one where the color change occurs within this range, this pH jump, and that would be methyl red, and phenolphthalein would be the choice of indicators for determining the equivalence point. You would not use thermal blue because you'll notice here that the color change for thermal blue falls outside of that pH jump that you see here in the pH curve, all right? So this underscores the importance of the correct choice of indicator that you'd use based on the type of titration that you're doing, all right? So if you're using a strong acid, or if you're doing a strong acid, strong base titration, then these two indicators would be suitable, all right? And this would not be, okay? So that's basically that as far as indicators being used to indicate the equivalence point of a titration of a strong acid or strong and strong base. So let's look at this example. It says, which indicator would you use for the titration of nitrous acid with potassium hydroxide? So the question you have to ask yourself is, what type of acid is nitrous acid? And you would say what? What type of acid is nitrous acid? Remember, there are 6 strong acids that you need to memorize, right? So would nitrous acid be one of them? No, it's a weak acid, right? So here we have a titration of a weak acid, which is nitrous acid, with potassium hydroxide, which is a strong base. All right. So therefore, the question is, which of these indicators would you use based on the pH range over which the color change would occur for each of these, right? So weak acid is titrated versus a strong base. So the question you have to ask yourself is, okay, so what would you expect the pH be at the equivalence point? So if you're titrating a weak acid versus a strong base, you'd expect the pH to be greater than 7, all right? So if the pH is greater than 7, right, that means that you'd use an indicator whose color change would occur above 7. So which of these indicators would you choose for this type of titration?
The last two.
The last two, exactly. Cresol red and phenolphthalein, because their pH values, well, this one is just slightly under 7, but still can be used for that purpose. And definitely you can use the phenolphthalein. So the answer is you can use Cresol red or phenolphthalein, all right? Okay, so I think now remember I said that the last question in assignment 4 will be the first question in assignment 5, all right? So let me hand these out to the guys. All right, so the first question I think we did before, you can just rewrite it on in that space provided. And let me see if I can bring up that same assignment on the screen. There's nobody online, so I don't know. Let me oh shoot. Okay. It looked like I jumped the gun in terms of the recording. Okay, so let me go here. Let me go to files. And let me go to assignments. And let me go to what is it now? Assignment number 5. And download. Okay. So we did number 1 already, but that was the last question in the previous assignment, which I told you guys I would transfer to this assignment. So let's see, number 2. Okay, so let's look at number 2. Number 2, did we do this one? This one looks familiar. Anyway, I'll do it. Okay, so this question says you're to calculate the pH of a 0.25 m sodium formate solution, given that the value of Ka for formic acid is 1.8 times 10 to the minus 4. So they gave us the value of Ka. So for formic acid, which we don't need to look up since they gave it to us. Okay, so the first thing I would do is write down what will happen when sodium formate is dissolved in water. So again, I'm just going to use NaA to represent sodium formate. So sodium formate will dissociate to form Na plus A minus, and then the A minus will react with water to form OH minus plus HA, right? So initially, we would have 0.25 M of the A minus. You'd have none of this. I need to make a correction here. This should be minus. Okay, what am I doing? Okay, so this would be OH minus plus HA, right? You'll have none of that. The change here would be minus X plus X plus X. So that at equilibrium, you're going to have 0.25 minus X. Here you're going to have X, here you're going to have X. So KB, because this is acting as a base now, we have to write down the KB expression, which is equal to X squared over 0.25 minus X, right? Now, again, we're going to assume that X is much less than 0.25, which means that KB is equal to X squared over 0.25, which means that X is equal to the square root of KB times 0.25. Now, you will not find KB in the tables that I've provided for you, right? Because this is the sodium, KB is for the formate ion, right? What we need is to calculate KB based on the Ka of formic acid. So this is Ka, right? For formic acid. So how do we find Ka? Kw divided by?
We're trying to find KB.
We're trying to find Kb. So Kw divided by?
Ka.
Ka, exactly. Multiplied by 0.25, right? So this works out to be the square root of Kw, which is 1.0 times 10 to the minus 14, divided by Ka, which is 1.8 times 10 to the minus 4, times 0.25, and we need to work that out. So that would be 1 times 10 to the minus 4, times 0.25, and then divided by 1.8 times 10 to the minus 4. And according to my calculation, this works out to be equal to, when rounded off to 2 sig figs, make sure I'm saying the right thing. So if I'm running off 2 sig figs, this will give you 1.4 times 10 to the minus 11. All right, please correct me if I'm wrong, but that's what I got. So that's X, which will be equal to the concentration of OH minus. Now remember, the question is asking for the pH. I'm running out of space, so let me just erase the top part here. So if you, so now that we have the concentration of the OH, what's the next step? Because remember, the question is asking for the pH. So how would you find the concentration? How would you find the pH? This is the concentration of OH minus. So let me,
We have to do the percent.
oh yes, of course, which I think is going to be, let me do that first. Thank you. I'm quite sure it's going to be less than 5%. So, but let's play it safe. So, percent dissociation will be equal to 1.4 times 10 to the minus 11 divided by 0.25 m. Yeah, this is going to be less than 5%. So 1.4 times 10 to the minus 11 divided by 0.25 times 100. So, we'll do this again. 1.4 times 10 to the minus 11 divided by 0.25. Okay, so according to my calculation, times 100. Sig figs. So according to my calculation, this is going to be 5.69, 5.6 times 10 to the minus 9%. So obviously less than 5%. So therefore, assumption is okay. So now we know that the concentration of OH minus, as I said before, is 1.4 times 10 to the minus 11. And remember, the aim of the question is to find the pH. So how do we find the pH from here?
POH.
Okay, so pOH, this is M, is equal to minus log of 1.4 times 10 to the minus 11. So let's see what that gives. 1.4 times 10 to the minus 11. Find minus log of that. So according to my calculations, when rounded off to 2 decimal places, that would be equal to 10.85. So what next?
You subtract that, 14.
To get a pH, right? So 14.00 minus 10.85. And that would be equal to 3. Wait a minute. Something is off here. I'll have to recheck this question. Okay. No, the reason why I'm hesitating is because the solution should be basic and the pH should be not less than 7, but I have here 3.15. So I have to recheck. I thought I had worked it out. Oh. Okay, so it looks like I made an error here. Let me work this part out again. It's 1 times 10 to the minus 14 times 0.25 divided by 1.8 times 10 to the minus 4 equals, oh, I forgot to do the square root. So this should be 3.7 times 10 to the minus 6. Okay, so let me erase this here. So that should be 3.7 times 10 to the minus 6. And that would change a whole lot of things as well. So this should be 3.7 times 10 to the minus 6 m, which means that this would have to be changed right here. This is change here and here. So this should be 3.7 times 10 to the minus 6. This would be 3.7 times 10 to the minus 6. I knew something was wrong. And then find the minus log of that. So this would be 5.42. And that will change this here. 5.42. And that will change this here. So that's 14. And that is 8.57. That is more like it. That is above 7. So
I got 5.43, 5.42.
Well, you got what, 5 point what
5.43.
here?
Yeah.
Let me do it again, 3.7 times 10 to the minus 6. I find the log. Oh yeah, you're right, 5.43. So this should be 5.43 here. So let's see now. 8.57 would be the answer. 8.57 would be the answer. All right. So that's basically how that is done. Okay, so this kind of underscores the importance of being careful because, as you can see, making one mistake here would result in incorrect answer. And sometimes, what I would suggest you guys do is that when you're doing these problems, try to see if the answer makes sense. For example, in this case, I knew that this solution is going to be basic because the base is producing hydroxide ions. So therefore, I knew that the pH has to be above 7. So when I got a pH below 7, I knew that I made some mistake somewhere along the line. So you just have to be careful when doing these kind of problems. Okay, any questions about this? Any questions? Any questions? Okay, let me clear this. And let me see if we can do any other questions. Okay, let's look at it's almost time. All right, tell you what, we'll stop here for today. And we'll continue tomorrow with question number 3.